In this video, we're going to start our section on the divergence theorem. Our goals are to learn what this theorem is and how we can apply it to more quickly compute the flux of a vector field around closed surfaces. So the divergence theorem, which is sometimes also called Gauss's theorem, will generalize Green's theorem, but to three-dimensional space. So let's first quickly remind ourselves, what does Green's theorem say? So let's flip it back in our notes a couple pages. Let us flip it back. Let's flip it back. So with Green's theorem, we were talking about a closed curve in the plane. So a curve that starts and ends at the same spot. And we were drawing our unit normal vector oriented outward from that curve. And what it said was, if we want to calculate the flux of that vector field across this closed curve, that's going to be equal to the double integral over this internal region, which we're calling R, of the divergence of that vector field. Okay, so this new theorem, the divergence theorem, is going to generalize this. So instead of taking the flux across this closed curve in the plane, now I'm going to do the flux across a surface. And that surface is going to enclose a three-dimensional volume rather than this two-dimensional area. Okay, so let's flip it back to where we were, and let's draw a picture. So now I'm going to have this closed surface. I'm going to call it S. So let me draw this surface. I'll have this closed surface. I'll do my best to make it look 3D. So I'll draw one of these, maybe a cross section here. And once I get to the back, which I can't see, I'll draw with a dotted line. So I have this surface, S, this surface. And this surface is enclosing some three-dimensional volume, this region. I'm going to call it D. So this is this 3D region that is inside the closed surface. Okay. And I'm going to, again, have this outward oriented normal. So I'll draw a couple of normal vectors. So these are perpendicular, unit normal vectors, perpendicular to my surface. So outward oriented normal vectors. My normal vectors. So if I have a vector field now in 3D space, and the components, the m, the n, and the p, if they have continuous partial derivatives throughout that region D, then if I want to find the flux across this closed surface, so I'm going to need a surface integral for that, and then I draw this little circle through the integral, that indicates it's a closed surface. Now instead of having a double integral, because D is 3D, I need a triple integral. It's going to be equal to the triple integral over D of the divergence, which I can write as this del dot my vector field, and then I write dv for my triple integral. And remember what the divergence gives me is, it's going to do the partial of this first component with respect to x, so partial of m with respect to x, and then plus, then the partial of that next one with respect to y, so partial of n with respect to y, and then plus the partial of p, the partial of p with respect to z. Okay, so let me go ahead and highlight this. Let's highlight this theorem. All right, so one of the ways that I can interpret what this is saying is, if my vector field represents the flow of some fluid, or maybe it's the movement of some gas in 3D space, then this right-hand side with the divergence says that the total expansion of that fluid, because that's what the divergence is kind of telling me, how much is this fluid kind of expanding away from the point or converging into it. So that total expansion of the fluid ends up equaling just the total flux out of the boundary surface. So the reason why is very similar to what we saw with the proof of Green's theorem, that if I cut up this region into a bunch of tiny boxes, that internally there's a bunch of cancellation when I add up these divergences. And all that kind of survives is what's happening on the boundary. And that's why we're left with just this flux surface integral. Okay, so let's do a couple of examples. So first, let's suppose that I have a rigid container filled with gas. So that means this container is fixed in size. It's not going to get bigger or smaller. But if the gas starts to expand, but the container does not, what has to happen? So, okay, if my gas is expanding, if the gas is expanding, this means that the divergence, so if I have a point and then the gas is expanding, my vector field arrows are pointing away from it. That's a positive divergence. So this means my divergence of f, that's going to be positive. And if that's happening everywhere in the region, well then this triple integral, my function inside is always positive. So the triple integral is going to be positive. Okay, so this means that the triple integral over that region D of my divergence of f dv, well, that's got to be positive. But the triple integral, that's equal to this flux surface integral. So this is equal to that flux surface integral. I'll put this little circle through it because it's a closed surface of my f dotted with that unit normal vector ds for surface integral. Well, that's got to be positive because these two integrals are equal by that theorem. So, well, this is saying the flux is positive, and because my normal vector is pointing outward, that means this fluid or this gas is moving out of the container. It's flowing out. Okay, so that means that gas is leaking out. Whoops, gas leaks out. Okay. Okay, all right, let's do one more follow-up to this. So now let's suppose that we go to the gas station and pump air into one of your car's tires. Assuming the tire is rigid and doesn't expand, what has to happen to the air inside the tire? Okay, so, you know, this is not a great picture, but imagine that this 3D surface, imagine that's the boundary of my tire here. Okay, and so if we are pumping air into the tire, what does that mean? What is that going to tell us? So we have a net movement of air into the tire. That means the flux is going to be negative. So this surface integral, my surface integral of f dot my unit normal vector ds, well, that's going to be negative. It's going to be less than 0. But that surface integral equals this triple integral. So this is going to be equal to the, let me scroll down, the triple integral over d of my divergence of f dv. So that has got to be less than 0. And for this triple integral to be less than 0, that means this function inside, the places where it's negative, they got to outweigh the places where it's positive. So generally, this divergence function should be negative. So generally, for this to happen, this divergence has to be negative. And if that's the case, well, a negative divergence means that the gas, the air, it's converging into that point. In other words, it's compressing. So the air is compressing. The air is compressing. And if we do a reality check, I think that's what we'd expect to happen. If we're pumping air into our tires, the more air we pump in, the higher the pressure builds. That's because the air is compressing. So in our next few videos, we'll do some examples where we actually need to use this theorem to find the outward flux across closed surfaces.